Hello, everyone. Good morning. We are very pleased to be here today to share our work on using Copernicus Earth observation data to support local scale climate services. So in this presentation, I will show you how we move from Copernicus data layers to producing local climate zones classifications, which are crucial climate informed for urban planning, risk assessment, and policy development. I will walk you through the problem we are addressing, the methodology actually developed by Ana Oliveira, and the tools we are building to make this process scalable and accessible at Plus Atlantic. So, a bit of who we are. This is not up. Now it's working. Thank you. So we are Plus Atlantic is a Portuguese non-profit R&D and innovation institution. It was established around 19. It was founded to advance integrated knowledge on ocean, atmosphere, climate across the Atlantic. This would be done by delivering knowledge-driven products and services in blue economy, marine science, climate adaptation, coastal resilience, and ocean sustainability. Of course, while prioritizing technological solutions like Earth observation, numerical modeling, remote sensing, artificial intelligence. So now into the problem. As we know, cities are increasingly exposed to multiple compounding climate risks. So we are seeing extended summers adding up to 50 extra hot days per year, pushing around 70% of vulnerable households into energy poverty. We also see heat waves lasting 10 to 20 days annually, becoming more dangerous in cities where we see around 12% of the homes only having air conditioning. At the same time, we see prolonged droughts that are fueling wildfire risks, and we also see short bursts of intense rainfall that threaten thousands of people and buildings with flooding and sea level rise. But what I want to highlight here is that these climate impacts are not evenly distributed, so they can vary according to the physical structure of our environment. So the visual that you see on the bottom of the slide represents a gradient of built and natural surfaces, from dense high-rise blocks to open low-rise areas, and also green or water-covered landscapes. Above this visual, you have the color bars that show examples of key climate stresses such as temperature and NO2 concentrations varying across these environments. So as expected, we see compact urban forms that tend to trap more heat and accumulate more pollution, while vegetated open surfaces help mitigate both of them. So this is to illustrate how urban morphology directly shapes exposure. So to respond effectively, we need, of course, to have spatial detailed information that captures these structural differences, and that's exactly what Land Copernicus data can help us on building local climate zone type classifications. So, how do we build a solution that translates this EO data into meaningful localized climate intelligence? It starts, of course, with the input data. That can be cartography, including terrain models, administrative limits, infrastructure layers, observation, of course, using sensors and IoT to monitor real-time environmental conditions, and finally forecasting, which gives us context from the background climate trends and future climate scenarios. So these data streams are brought together through integration mechanisms such as artificial intelligence, spatial modeling, and the result is, of course, a layer of added intelligence, enabling more informed, spatial-aware decision-making, not just what and when, but critically where to intervene. So by combining LCZ classifications with other layers, as the ones I mentioned, we can deliver added value climate forecasts tailored to urban morphology, We can be more precise on risk assessment inputs, such as localized vulnerability to heat or pollution, and scenario tools to test planning strategies under different urban and climate futures. So this system-level approach would support cities in designing evidence-based, local-specific adaptation strategies. So now, what are LCCs and what do we need? To address the spatial differences of the climate risks, we need a framework that captures the physical characteristics, and that's where local climate zones come in. So LCCs classify the urban and natural landscape into standard types of dimensions. There are four. One of them is the height of the surface features like buildings and trees, the density or packing of those features, the surface cover surrounding them, such as concrete, vegetation, bare soil, and the thermal properties of the materials involved. This classification helps us understand how different parts of the city respond to different climate drivers. Continuing. Here you see a complete classification scheme of the local climate zones. This system was initially developed by Stewart and Oak. So they provide a standardized typology to describe the urban and natural environments, as I was saying. On the left, we have the build types ranging from compact high-rises areas like city centers with dense vertical constructions to lightweight or open low-rise structures found in suburban or informal settings. These categories reflect both morphology and material, which directly influence thermal and pollution dynamics. For example, how much heat is retained, or how air circulates, or how surface runoff behaves. On the right of the slide, we have the land cover types, including forested areas, shrublands, grasslands, bare surfaces, and water bodies. These natural types are equally important as they regulate many aspects of our environment, such as evapotranspiration, shading, air quality. And this is what makes LCZ powerful because of their global standardization that allow us to map and compare every urban environment if we use the same methodology. So into the workflow and what we actually did at Plus Atlantic. So of course, initially the workflow begins with the collect of input data. The base layers of this methodology are Urban Atlas and Core Inland Cover. Then we also have adding information, the tree cover density, the dominant leaf type, grasslands, and impervious density. We also have an optional layer we can use for the OpenStreetMaps to infer building height. Then we go into the pre-processing of the data, so harmonize every data set with each other, merge it with the Urban Atlas and Core Inland Cover, making it a baseline polygon layer. Then it's enriched by the high resolution attributes. So all of these inputs are reclassified using rule-based rules that allow us to infer where each classification goes. This is all done initially in Archie's toolbox. You can go into the paper that was provided in a website where this is all described. And you can see also that this was tested in 5 southern European cities, so Athens, Barcelona, Lisbon, Marseille, and Naples, and achieved 80% overall accuracy. Here in this diagram, we show how different land covers, so essentially the workflow of the reclassification. So the land cover and the land use data sets are combined and then reclassified into the LCZ categories. On the left side, you see the input layer, so primarily Urban Atlas codes. And in the middle, you see how these classes are enriched with the ancillary layers. So the grassland, tree cover density, OpenStreetMaps, to then refine the classification, particularly in areas with ambiguous or mixed type typologies. So on the right, this includes flow into aggregated classes such as LCZ 1 to 3 for compact building built-up areas. Then you have LCC A to D for different types of vegetative surfaces, LCD 10 for heavy industry, and then the other remaining classes. As an example, we have the first urban atlas class, which refers to continuous dense urban fabric, which is directly linked with LCZs 1 and 3, depending on the structural attributes like imperviousness and cheek cover. In contrast, the class 2003 23000, it's easier for me to say like this, representing green areas, flows towards LCZD, linked with low plants and managed grasslands. So this rules-based classification allows for a deterministic, scalable, and interpretable translation of Copernicus land products into the LCZs. We give you here some, as I said, and apply this to different cities, because these are cities that are suffering of intensifying summer heat. They clearly differentiate, as you can see, compact urban cores, mixed-use areas, industrial zones, and this special detail allows us to analyze pattern of urban heat exposure, pollution hotspots, or green space deficits. I'll go and show you an example. So here we see a real application of the LCZs in Naples, where we explore the relationship between urban form and temperature during the day. On the right, you see an image of diurnal land surface temperature mapped with Landsat 8. And on the left, you see LCZ classification map that highlights the distribution of the built-in land cover types. The chart in the lower left plots of the diurnal surface urban heat intensity across LCZ types. It shows that you don't see a huge contrast during the day, but then when we look at the night picture, you see a much bigger contrast. So this is also reflected by the plot that you can see on the left. The reason essentially lies on the thermal inertia of the dense urban materials, so concrete, asphalt, that store heat during the day and then release slowly during the night. Now, to make LCZ mapping more accessible to everyone and operational, we are building a platform. This platform will allow users to generate LCZ classifications for any European region of interest through a guided interactive interface. So the first thing you need to do is defining a region of interest. You can interactively select an area by drawing, and in the future we want to also add the possibility of you inputting a shapefile or something that relates to the extent that you want to see classified. Here is just a brief overview of how the processing is done. So you can also ask for a specific type of output format, and the awaiting time, of course, will depend on the queue in size. Here is just an example of a classification done manually in ArcGIS and on our automatic platform. You see no major differences. So we were able to quickly solve it and automate the LCZ classifications. And also this was, of course, validated. And So the platform generates 50 reference points per class, selected through a stratified random approach. These points are then compared manually or referenced with LCZ labels, allowing us to compute common accuracy metrics such as overall accuracy, that in this case yields a 90%, and kappa coefficient that in this case yields 96%. One interesting finding is that LCZ10, so heavy industry, constantly show the lowest classification confidence. So it's a tricky class to yield. So essentially what's next is to build a participatory WebGIS platform where users can make their own validation. They can gather more than 2 or 3 years of information, and is eventually create a machine learning algorithm to improve classification using supervised classification methods. And also the expansion of LCZ outside of Europe, because Copernicus allows us to do that. So this will be one of the next steps. Thank you very much. This is it.
Thanks a lot, Inês, for your presentation. So we will go to the Q&A session with Inês and Anna, so both of them. Okay, so the first question being, is your data applicable to any cities globally or European cities only?
I guess that this last slide answered this question. Essentially, now we can do it for Europe, but we are developing to make it possible globally. Yes.
Okay. Okay, thanks. Next question, do you have information about vegetation quality? Same question for substrate Q.
Not in this workflow. We don't consider the vegetation quality, although we do consider types of vegetation, not the quality.
Okay. The next question, is the classification pixel-based or object-based?
So when we are computing some of the classifications, we use area-based. Although we are working with pixel-based, so rasters, we do use areas to compute this information, because if we were using only pixels, we would yield 100% of everything in each pixel. So we need to consider a bigger area to compute the statistics. Yes.
Okay, thanks. Makes sense. Up to the next question. Could these urban atlases be processed also with QGIS?
Well, so Ana Oliveira developed this in ArcGIS. I believe that because of that, you are able to implement the workflow in QGIS, although I believe that would take you a bit more and would be processing heavy.
Okay. Okay, thanks. The next question, so is it possible to compare the same area between 2 different periods, for example, after 2 weeks of dry and warm season versus 2 days after 60 millimeter day precipitation?
Okay, so this workflow and the local climate zones are computed based on yearly inputs. So you of course can compare it, but you will be using time fixed information. So for that year, so if you compute LCZs for different years, you could then make different comparisons. But in this case, it's a yearly timed fix, let's say. I don't know, Anna, if you want to add anything to this. Feel free.
Do you have any idea of much time it will take to launch globally?
Not for sure. We are working on this. We are starting to work on this, and I would believe that Maybe next year we will have it operational and public available.
Okay, thanks. Thanks for the precision. Okay. What is your reference data set for accuracy assessment?
I would
Inês,
say,
maybe I
yeah.
get this one.
Yes, please.
So because this one is actually done back in 2019. So for reference accuracy assessment on the original methodology, we selected random points and we visually inspected the site. So it was manually inspecting site by site in terms of the actually local climate zones. Concerning the platform in itself, it's different. So because the idea is for the open platform to replicate the original method, so the target reference data set is the previously published LCZ maps that you can find in the original papers. So it's different. You have all the details of this and the published materials, and yeah.
Okay, thanks. Oh, and another question, can QGIS tools on WEkEO help in mapping local species or habitat zone? So concerning the tools available on WEkEO, you can try to do that on your side. I don't know concerning your project, Anna and Inês, if it could be like kind of replicate to another like the question, so for species or habitat zone, can you think you could use your project to yeah?
Should I answer, Anna? Will you? Yeah. So, well, in the concept of local climate zones, of course, it would be since I'm a scientist, it would be very curious to compare with species or habitat zones. Of course, it could have added value, but I don't know at which point it will give you input on habitat or species, because this also considers urban areas. So I would say that you would need to input other information to be able to map local species or habitat zones, but for sure would be an added value classification, yes.
Okay, thanks a lot. That's it for the question for your presentation. So thanks again to both of us for joining us.